Hello and welcome back to my Physics Online Video Lecture Supplement series. In today's video, I wanted to continue with the sixth set of lectures, which are on the topic of uniform circular motion and motion in circles and orbits and so on. And specifically, what I wanted to look at in today's video is the third part of this set of lectures, which pertains to the models of the solar system, and in particular to Kepler's model of the solar system and to Kepler's laws. But before we get to Kepler's laws, I thought it'd be kind of interesting to look at a few of the different models of the solar system which existed around the time of Kepler. Now, Johannes Kepler was an astronomer and a mathematician, and he was basically around about the same time as another famous astronomer, physicist, mathematician named Galileo Galilei. And actually, their models of the solar system were sort of competing models, Galileo's model actually being the model of his mentor Nicholas Copernicus. In any case, there were a variety of different models which existed, and you can see here a little picture that shows several of them. The earliest models that I know of date back actually, I believe, to ancient Greece and were heliocentric, believe it or not. That means that they put the sun at the center of the solar system. But it was not a very scientific model, in that it was basically based on the Greek belief at the time that the sun was basically made out of fire, which I guess is not too far from the truth, but more specifically that fire is the most perfect of their four elements, and therefore that it belonged at the center of things, and so that's why the sun was at the center and the earth went around the sun. It's not a very good explanation as concerns science as we understand it. Maybe that cut it then, but the problem is that it wasn't really based on any real observations that were done in the modern scientific sense of the word. It was more of a mystical definition for why, or explanation for why the sun must be at the center. And so it was a little while before any of these Western nations, and I'm including here Egypt and Greece and even some of the Middle Eastern things as being sort of Western nations, if you will. It was a while before any of them really got around to observing the positions of the stars and using those observations to attempt to formulate some sort of a model. And as far as I know, the first attempt at this modeling the solar system based on observation would date to Ptolemy of Alexandria. Now, by the early 17th century, this is about the time of Galileo Galilei, there were actually about 7 serious models of the solar system which had been proposed. And this 17th century, so a little timeline, Galileo basically would have flourished from the early and mid 17th century. Basically, he was the student of Nicholas Copernicus, who is quite probably the greatest astronomer of his time. In the previous century, the 16th century. And basically what happened is that there were about 7 different serious models of the solar system which had been proposed and which were sort of being considered during the turn of the 17th century. So I'm going to list them in not necessarily chronological order, but rather in sort of order from how heliocentric they are, if you will. So the first model, of course, the oldest one, is the familiar geocentric model of Ptolemy. And that's the one that basically puts the Earth in the very middle of the solar system and then puts everything going around the Earth. The Earth is totally stationary. It does not move. It does not rotate. It just sits there and everything goes around it. And of course, this was basically modified as observations showed that there seemed to be retrograde motion of some of the planets. And so there were some basically modifications to it over the many centuries between the time of Ptolemy and the time of Galileo. And so then another version of this sort of geocentric system would have been the Heraclidean system. This one is maybe the first of what could be called a geocentric heliocentric, or a geoheliocentric or heliogeocentric model. Basically what this is, and there's sort of a sketch of it over here, is that you put the Earth in the middle, and the moon is going around the Earth, and the sun is going around the Earth. And the two innermost planets, Venus and Mercury, are going around the sun, which is itself going around the Earth. And then the outer planets, Mars and Jupiter and Saturn, these were the known outer planets at that time, were going around the Earth. So this actually is a sort of a sketch that's taken from the annotated version, Paul Wittick's annotated version of Galileo's book De Revolutiones, in which he was explaining the Copernican model. So this is also a heliocentric model, a geocentric model, but it is a geocentric model which also has some heliocentric elements in that there are some planets orbiting the sun in this model. All right, so those are our first two. Let's look at a few more which are more or less heliogeocentric. This first one actually is not heliocentric so much as interesting in that it has a rotating Earth. And this one might be called the Gilbertian model. It's essentially geocentric, meaning the Earth is in the center, but the Earth is not necessarily entirely stationary. The Earth is rotating. The Earth maybe even is moving about or wobbling about beyond just rotation on its axis. And it's actually interesting to note that similar models to this existed, or at least were discussed, in the late Middle Ages, even at the Sorbonne, which was the University of Paris, one of the most famous universities of the time, which we actually sort of encountered in an earlier set of lectures because it was the university at which Jean Buridan taught. So you can refer back to the previous set of lectures on Newton's laws for a little more on that. Actually, the interested reader might do well to read Pierre Duham's classic work on the development of science, basically through the Middle Ages and up into modern times. In any case, the main champion, if you will, of the rotating but stationary Earth, totally geocentric model would be the one by William Gilbert. The next model that's of interest is the Tychonic model, and this is what is pictured here in this particular image. This one places the Earth at the center of everything, and the moon goes around the Earth, the sun goes around the moon, and all the other planets that were known at the time would go around the sun. So you can see that this is somewhat different than the Heraclidean model that was also championed by Wittig that I had on that previous slide, in that on the previous one, only Mercury and Venus were going around the sun as it went around the Earth, and all the other planets were just centered on and orbiting around the Earth. This one has most of the planets centered on and orbiting the sun, with the moon orbiting the Earth and the sun orbiting the Earth. And so this was by Tycho Brahe, who was possibly the other greatest astronomer of the late 16th century, along with Copernicus. The sort of a student of Tycho Brahe's, in the sense of that he basically borrowed his model from Brahe and then slightly modified it, is the Ursine model. This is by Nicholas Reimers Barr, who was a royal astronomer in the late 16th century, who was known as Ursus. And he basically took Tycho Brahe's system and modified it only by having a rotating Earth. So the Earth rotates on its axes, and other than that, it's the Tychonic system. So in fact, this model that I'm showing over here that I've labeled the Tychonic model could just as easily be the Ursine model, so long as you keep in mind that the Earth is also spinning. And before I jump to the two true heliocentric system models of the solar system, I should add a point of interest, which is that this system, this model here, would look very similar, in fact, and the observations would look very similar to those of a basically stationary sun in which everything orbits the sun. It's just basically a bit of a shift in who you count as the observer. And in fact, you can get very good data and even can make nice trajectories based on these models, or based on a slightly modified version of these models, which is that the orbits aren't actually all circular, and in fact neither the sun nor any of the other planets is actually truly stationary. The sun actually wobbles a bit, and so the Earth would actually also wobble a bit in this model. But I actually have been given to understand that some of the of the NASA calculations that they do can use something like this model for simplicity's sake, even though the generally accepted model is not this one. So I found that as an interesting historical tidbit. All right, so let's look at these heliocentric models of the solar system. The two true heliocentric models are the Copernican model and the Keplerian model. In the Copernican model, you have the sun sitting at the very center, and everything ends up orbiting the sun, basically, in more or less circular orbits, although if you look at the little diagram down here, you'll also notice that the circular orbits are not necessarily all centered on the sun, and you'll notice that there's sort of circles within circles. These are called epicycles. And this is basically a comparison between the Ptolemaic model and the Copernican model. And you can see that there's actually quite a few epicycles in the Copernican model. It's really not a simpler model than the Ptolemaic model, as measured by how many weird epicycles does everything end up needing to make. You can even see some kind of funny epicycles within epicycles. You know, here's Mercury's orbit. It's basically going around this circle. It's making epicycles here, and the center of these epicycles is itself making an epicycle. That's what comes of trying to fit everything into a circle. It turns out that there's a seventh model that's heliocentric, which would be Keplerian, and it looks heliocentric, except for that instead of the orbits all being circular, they are in fact elliptical. And so the sun is placed at one of the two foci of the ellipse rather than at the center of a circle. I think it's kind of interesting, by the way, that basically none of these models seems, none of the previous models that was geocentric in one way or another, attempted to put elliptical orbits. I kind of wonder whether anybody sort of proposed that in it and then never really got it published, or what the historical record would show there. But it seems that most of the geocentric models ended up having more or less circular orbits with some epicycles, and then the heliocentric models, Copernicus basically continued with circular orbits and epicycles, and then Kepler made the big, for lack of a better word, you'll have to pardon this pun, revolution by adding elliptical orbits. So there we have it. That's our 7 different models of the solar system that were sort of the major models as of the early 17th century. So what happened? Well, Galileo Galilei and others actually made some observation. Galileo actually made one very crucial observation that I guess he was maybe the first person to notice, or certainly among the first people to notice. And that observation is that Venus has phases. The moon has phases, Venus has phases. This actually implied that Venus needs to pass behind the sun in some way or another. So if you have a purely geocentric system, this doesn't work. The Venus doesn't ever end up really being behind the sun, certainly not with the frequency needed to explain the phases of Venus. So what does this do? It eliminates a few of the models of the solar system, because Venus actually, in many of these, let's go back a couple slides here. Here's Venus's orbit around the Earth. Here's the Earth. Here is the sun's orbit around the Earth. And you'll notice that Venus at no point in this orbit would go behind the sun. There's no point at which Venus should actually be darkening and brightening in this model. So that basically eliminates the Ptolemaic model. It actually also ends up eliminating the Gilbertian model, because again, in the Gilbertian model, the Earth is, you could almost plop this thing down and then have the Earth spinning, and that maybe reduces or eliminates some epicycles. But basically, again, Venus never passes behind the sun with respect to the Earth. Okay, so what has happened at this point is we've got 7 different models that are based on observations of the stars and their motions. And what happens is that Galileo, as an astronomer, makes one very crucial observation. This is actually the only astronomical observation that is really significant that Galileo himself makes, and that's that Venus has phases. So he's among the first, if not the first, to notice that there are phases for Venus. And what does this fact that there are phases imply? Well, it implies that Venus must pass behind the sun with respect to the Earth. So let's go back and look at a couple of the models and see whether that's possible or not. So I'll pull up actually just this previous slide with the Ptolemaic model and the Copernican model. So here's the Ptolemaic model. Here's the Earth. Here's Venus. Venus is going around the Earth. It's basically on some sort of epicycles within epicycles orbit. And then here's the sun. And you'll notice that Venus never really passes behind the sun on this orbit. It's always going to be between the sun and the Earth, or off to the side with respect to the sun, that kind of thing. So this model predicts that there are no phases for Venus. Look over here at the Copernican model. Here's the Earth going around the sun, and then here's Venus, and it's entirely possible for the sun to be directly between the Earth and Venus. This means that it's possible, among other things, for Venus to have phases. So this model actually is okay with phases. This one is not. And so what actually happens based on that observation is that we can eliminate the purely geocentric models. That actually only eliminates two, Ptolemaic and Gilbertian. But the Tychonic, Ursine, and Heraclidean models all would still predict phases for Venus. So those models are still all in contention, as of course are the Copernican model that Galileo champions, and as of course is the Keplerian model. So what we have over here is an illustration that was made sometime after this observation came to pass. It's on the frontispiece of the Almagestum Novum. And what you can see here is a few of the models of the solar system being illustrated here. This is basically an angel that's weighing out two of the models. See if you can figure out what these two models are just by looking at them and which one this is. I'll give you a second to look them over before revealing the answer here. But basically, what you see here is this guy that's lying down on the ground back here actually represents Ptolemy. And essentially what's happening here is the angel is weighing out different possible models. And these two are sort of balanced right now in this diagram. So despite the appearance that this one's heavier than the other, it's actually, from the correct perspective, it's balanced, and he's trying to weigh them. This is Ptolemy. He's on the ground. You could say he's down for the count. Here's Ptolemy's model down here. So here's the Earth, and here's everything going around the Earth. They are basically saying, hey, we've eliminated this one. And if you look at these two models, you can see the Copernican model over here. The sun's in the middle. Everything's going around the sun. Here's the Earth. Here's the moon going around the Earth. This one is either the Tychonic or the Ursine model. Earth, moon, here's the sun. Here's everything going around the sun, with the sun going around the Earth. So if we fast forward a few years, you end up with three remaining viable systems: the Keplerian, the Tychonic, and the Ursine. Copernicus system, which is the one that Galileo was championing, actually faded in light of the superiority of Kepler's system. So Kepler's system just made better predictions. There were fewer epicycles. The planets all ended up where they were supposed to be when they're supposed to be there, in a manner that was basically better than what Copernicus' system did. So this might be a little bit surprising, and I suspect that someone along the lines must have modified the Tychonic and or Ursine systems to include the possibility of an elliptical orbit for the sun. Basically, Galileo dies towards the mid-17th century, and Isaac Newton is born. Actually, I think that he was born the same year that Galileo actually died. And before the time of Newton, we didn't have stuff like Newton's universal law of gravitation. If Newton formulated it, then we wouldn't have it until after Newton's been around for a little while. So all of this stuff was done without the universal law of gravitation. And when you take the context of Newton's laws, and in particular the law of gravitation, the Keplerian system actually makes the most sense, because we knew at that point that the sun was much, much bigger than the Earth, for example. I mean, you can read very ancient texts that figure out rough estimates for the size of the Earth. Certainly, I actually was recently reading a text by the Spanish Dominican Venerable Louis of Granada, and he makes some passing reference to the size of the sun as compared to the size of the Earth, and he very clearly understood that the sun was much larger. And this would have been in the basically late 1500s. So they knew this easily by this point in time. And in the light of Newton's laws, it becomes obvious that the sun should be more or less stationary because it's very massive, and everything else should be basically moving in orbits around the sun. And so that gave theoretical justification to Kepler. It was sort of lacking in some very important experimental confirmation. Basically, one of the problems with the geocentric systems was that what were called the fixed stars, meaning all the other stars that we observe in the sky that are very far away and therefore appear more or less fixed in their positions, compared to the planets, which seem to move across the sky. These so-called fixed stars could be observed through a telescope, and they basically, just by doing a simple calculation using simple geometry, would have appeared to be much closer than they actually were. Basically, the astronomers of the day would have assumed that, okay, all the stars are about the same size as the sun. Seems like a fair assumption. And they could measure the size that a star appeared to be through a telescope. And they could measure how large the sun appeared to be in the sky, and they knew about how far away the sun was. So simple geometry suggests that they could figure out how far away these stars were. The last problem, basically, that was faced by the heliocentric models was that the stars should have had some visible parallax if the Earth was moving and these fixed stars were not moving. And the reason why that was such a problem is that the astronomers of the day believed that these stars were much closer than they actually were. So one way of basically figuring out how far away a star is, so here's your astronomer. Let's say that this right here represents the sun. So how far away is the sun from some astronomer? One way you could do it is measure this distance to the star by knowing essentially what is the radius of this star, and then knowing how far away the star is. Kind of, you can set up a ratio by saying, okay, I look up in the sky, the star appears to be so large in the sky, I know that it's actually so far away. Now let's take a star which is even farther away, and as far as the astronomers of the day would have known, all stars basically are about the same size. That seemed like a valid conjecture at that time. And so if a star is farther away, then it's going to appear to have a smaller radius. And so you can do a bit of geometry to sort of predict how far away is the star based on knowing how large the sun is, based on knowing how far away the sun was, and then based on measuring how big a so-called fixed star is. So they knew that the stars were not infinitely far away. They basically had, again, a concept of how large the sun was and how far away it was, so you could therefore predict how far away the stars were. And it turns out that their predictions placed the stars much, much closer than they actually were. Basically, what happened is that they didn't observe parallax, which was an expected observation if the Earth is actually moving. And it turns out that the reason why they didn't observe that parallax, or the amount of parallax expected, is because the stars are much farther away than would have been predicted by this simple geometric argument. And the reason why that is that they were not taking into account stuff like the fact that the star is diffraction limited in size. And so you can measure some size to a star, and that's not the actual size you're seeing, thanks to basically diffraction, a topic in optics which wasn't really discovered for another 100 years or so. And also it took about that long before they were observing stuff like stellar aberration due to some sort of parallax. What all these observations ended up doing is allowed the scientists to conclude that these stars were many orders of magnitude farther away than they first predicted from the simple geometry. Hence, no observations of stellar parallax. Hence, the heliocentric model is now validated as possible. It hasn't been eliminated by this one bizarre observation that just wasn't making the model work out. So I should add, as a point of kind of curiosity of modern times, obviously the Keplerian system was eventually accepted as the correct one, and then we've made many modifications to what the solar system looks like, what the theory of gravitation looks like, and so on in the days since, for example, in the light of Einstein's relativity theory, and so on. It's worth noting, though, that there is still a small group of people out there who believes that we live in a geocentric universe. And their argument is basically somewhat difficult to summarize in a short video like this, but basically their argument is that if the Earth happens to be the center of mass of the entire universe, then it is possible for the Earth to be stationary while appearing to go around the sun, because in fact the entire universe is still orbiting about its center of mass. So with all that aside, what is it that Kepler's model basically ends up doing? Well, it gives us three laws ultimately, and he did this based on his observation, but also based on his mentor's observation. Tycho Brahe was actually Johannes Kepler's teacher, and so Kepler was Brahe's pupil and sort of inherited all of his observations, data, etc. In any case, he made three basic laws. The first one is the one that we've more or less been discussing, which is that all the planets move in elliptical orbits with the sun at one of the focal points of the ellipse. The other two laws are sort of in addition to that one. The first one says that if you draw a line from the sun to a given planet, then that line, as the planet goes around its orbit, is going to sweep out an equal area in an equal amount of time. So whatever area gets swept out by that line as the planet is moving in its orbit in 1 second, that amount of area will always be swept out in 1 second, no matter where in the orbit the planet is. The third law says that the square of the orbital period of a planet is proportional to the cube of the average distance from the planet to the sun. So let's look at these laws in a little more detail. So the first law, again, is basically the law that says that the planets are all going around the sun in elliptical orbits. What this basically means is that, for one thing, it's actually a natural consequence of Newton's law of gravitation. Let's say that you put the sun here, you put a planet out here, it has a given speed, but that speed is not the correct speed, such that this distance, the speed squared divided by this distance should give you the acceleration if it's going to be a circular orbit. Well, let's say that the speed is a little bit off, then you no longer have that circular orbit, and so the planet maybe starts to fall towards the sun because it's moving too slowly. And so it's speeding up as it falls towards the sun, but this is still sort of a centripetal force. Gets to this point that's nearest to the sun, and all of a sudden it's going too fast for a circular orbit. And so although the sun is still pulling it in, there's not enough centripetal acceleration to keep it in a circle, so it sort of falls out away from the sun, if you will. And so most of the planetary orbits are elliptical, but they are fairly close to being a circular as an ellipse. And basically, you can draw the orbit, or you can draw an ellipse by sort of imagine taking a rubber band, wrapping it around two different pins that are stuck into a piece of paper, and now you take a pencil or a pen, you hook it through the rubber band, and you basically try to draw around these two tacks, if you will. Basically, the shape that that pen or pencil will make should be an ellipse, and the two tacks are basically at the two focal points. All right, so that's Kepler's first law in a nutshell. Second law is that equal areas and equal times law. So imagine drawing a line from the sun to this planet, and as the planet moves, this line is going to be sweeping out some area. The line maybe moves from here to here, so the area enclosed would look like sort of a triangle, albeit with an elliptical edge rather than a straight edge for one side. All right, so here are three possible areas that get swept out by the planet. And basically, because the planet goes faster as it gets closer to the sun and slower as it gets farther away, that means that it will travel through a greater arc length when it's in close to the sun and a lesser arc length when it's out far away from the sun. And so the small arc length ends up having sort of a large radial distance. And so if you computed this area, it's going to be equal to this other area where you have a large arc length but a very small radial distance. And so each one of these areas is swept out in the same amount of time. We'll actually come back to this idea when we study angular momentum in a future lecture. Kepler's third law basically tells us that the square of the orbital period is going to be always proportional to the cube of the distance between the planet and the star, where the distance maybe is the average, for example, average radial distance. So you can get that by basically this is giving you the period in terms of some constants, where these constants are basically 4, you know what pi is, 3.1415, etc. G is the gravitational constant that was discussed earlier in the context of Newton's law for universal gravitation. M is the mass of the sun or whatever's being orbited. And then R, of course, is the distance between object and sun. So all these things are constant. That means that you can set up a ratio as follows. Since you have that the period squared is a bunch of constants times the radius cubed, you can just as easily write that period squared over radius cubed is all of these constants, 4 pi squared over gm. Since all of these right here are constants, this whole thing must be constant. And so that means, therefore, that t squared 1 over r1 cubed must also be t2 squared over r2 cubed. And the beauty of this third law, Kepler's third law, is that it's not just true for a planet orbiting a star. It is, in fact, true for any satellite which is orbiting a larger mass and which is orbiting that mass basically kept in orbit solely by the gravitational attraction between the two masses. What we have here is a table that compiles some orbital data for the moon, the sun, and the 9 primary satellites of the sun, with that last satellite being basically Pluto, which is once upon a time was a planet and now has been sort of redefined as a dwarf planet because they decided that basically that Pluto did not satisfy all three criteria of a planet. The third criteria is the one that it doesn't satisfy. Basically, it's supposed to sweep its orbit clean of other debris. This table, incidentally, despite including Pluto, ends up not including any of the various moons of other planets. It doesn't include the other dwarf planets that are in and near our solar system, etc. But what it does tell us is it gives us a mass, it gives us the mean radius, it gives us the orbital period, it gives us the mean distance from the sun. And so here are the calculated t squared over r cubed values, and you can see that they're all very nearly the exact same. They vary basically in the third significant figure. So consider this a theory that has held up pretty well. So there's actually a couple of simplifications that we've made, and I've kind of hinted at these earlier in today's video, which is that in reality, when you have a small mass orbiting a much larger mass, we assume, or we simplify the orbit to say that the larger mass is totally stationary and that the smaller mass is the thing that's actually going around the orbit. That's not quite true in reality. This little diagram is showing some examples of that, basically. What happens is if you have just two bodies, then the two bodies together orbit the collective center of mass of the two. Now, if one body is much more massive than the other, then that center of mass often tends to be inside the larger body. But as you could see in just the Earth-Moon system, the Earth would actually be going about a small orbit around the center of mass, and the Moon is also going in a small orbit around the center of mass. One thing that results in is that the Earth kind of wiggles as it goes around the sun, thanks to this little center of mass orbit between the Earth-Moon system. The other simplification that we make is that the system is isolated from other masses, so we can neglect small effects that are produced by outside masses. For example, in our own solar system, the Earth also is attracted to the Moon and vice versa, hence the little wiggles around the sun. But there's also plenty of other large planets out there like Jupiter or Saturn and relatively close planets like Mars or Venus that can also have some effect on our orbit. The reason why we make this other simplification is that it makes orbits much easier to deal with. And in fact, the three-body problem as opposed to the two-body problem is not very solvable in an analytic manner. Two-body problem is like Earth plus Moon. Three-body problem is like Earth plus Moon plus Sun, for example. You can solve this two-body problem analytically, as it turns out. You can't really solve this one totally analytically. You end up having to do some like simulations to do this. And by and large, within our own solar system, you always end up typically having one very large mass and one very small mass nearby, with other masses being far enough away that you can usually make a good approximation in a two-body system. However, in some extrasolar systems, it is possible to have a binary or trinary star system or binary black hole system or etc., in which both stars might be of comparable size and a third star is also in the system and all three are of comparable size. Or it's possible for planet and its moon to be comparable size, and for a star to also have a substantial effect on the orbit of the planet and the moon. So we basically have to make these simplifications to solve analytically to solve these kinds of problems that we're dealing with. All right, so let's look at a few short examples to close ourselves out. Our first example says that the average distance between Pluto and its largest moon is about 19,600 kilometers. We want to know what is the orbital period of this moon around Pluto. Okay, so to get the period, we're basically looking for what is the orbital period, that would be T, of this moon. The moon, by the way, is called Charon. And so what we're given in the text here of the problem is the radius. So r is approximately 1.96 times 10 to the 7th meters. Notice that this was in kilometers, so we need to convert it into meters. And g is the gravitational constant. So g is approximately 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And so all we need to do is find the mass of Pluto. So this right here would be mass of Pluto. And to get that, we need to pull up our notes or our text and find the table that has useful planetary data in it. So in our notes, that was table 6.3.1. So we need to locate Pluto, and here's the mass in kilograms, 1.27 times 10 to the 23rd. So M is 1.27 times 10 to the 23rd kilograms. So at this point, it is now a plug everything in and calculate it kind of problem. So T is going to be the square root of 4 times pi squared times r cubed, so 1.96 by 10 to the 7 meters quantity cubed, divided by 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, and then that is times 1.27 by 10 to the 23 kilograms. And so whip out your calculator, plug all these guys in. So let's see here. We have 4 times the pi squared times 1.96 by basically, let's actually multiply it by basically cubing it. Okay, and then that's going to have to be times 10 to the 7th cubed. And so this should give us the numerator. Can divide that by 6.67 times 10 to the minus 11. Okay, and then we got to divide that by 1.27 times 10 to the 23rd. All right, come out with a giant number, take the square root of that giant number, and we get 187,326 seconds. So let's just call it 187,000 seconds. All right, for our second question, we want to get the geosynchronous satellite. It's orbiting the Earth once per day. We want to know how high above the Earth is such a satellite located. And this is actually sort of more of a back of the envelope type calculation as opposed to the more rigorous calculation that you might use using Newton's laws, Newton's universal law of gravitation, etc. So in order to solve this problem, we can use the Kepler's third law again, and basically we're wanting to complete one orbit per day. So the period of the orbit is basically 1 day, which is, if you do the quick conversion, 86,400 seconds. All right, so that gets us T. The mass must be the mass of the Earth. And so we need to whip out that table from our notes again. So the Earth has a mass of about 6.42 times 10 to the 23rd. It's Mars. Earth has 5.98 times 10 to the 24th. So we need that mass. So 5.98 times 10 to the 24 kilograms. G, of course, is again the gravitational constant. So 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So basically we're looking for the value of R. So it looks to me like R should be the period squared times gravitational constant times the mass of the Earth divided by 4 pi squared, and then we're going to take the cube root of all that. Okay, so 8.64 times 10 to the 4th seconds, quantity squared, times 6.67 by 10 to the minus 11 Newton meters squared per kilogram squared, times this mass of the Earth divided by 4 pi squared, and again cube root of all of this, so to the 1/3 power. Pull up our calculator. Let's put these guys in. So we have 8.64 times 10 to the 4th, which has to be squared, and then that's got to be multiplied by 6.67 times 10 to the minus 11. That's got to then be multiplied by the mass of the Earth, so 5.98 times 10 to the 24. Okay, divide that by our 4 pi squared. And now we need to take a cube root. So I've come up with 42,250,000 meters. So R is, let us say, 42,250,000 meters, which would be 42,250 kilometers. Not a bad estimate, because very often it turns out that the height of a geosynchronous orbit for these satellites can be in the range of actually about 42.2 million meters. Last but not least among our examples, let's try to calculate the mass of the Sun based on the Earth's orbital period. All right, so in other words, we're looking for this term right here. So this is mass of Sun. And we know what the Earth's orbital period is. This is actually 365 as it turns out, 24 days. This extra 0.24 is where all of our leap year rules come from, by the way. And this right here ends up being the mean orbital radius for the Earth. And we can look that thing up in our table. Basically, this is the same as the mean distance from the Sun, and you can see it's 1.496 times 10 to the 11 meters. So let's go ahead and write that down, 1.496 times 10 to the 11 meters. Let's go ahead and convert the period from days into seconds. So 365.24 days times that 86,400 seconds per day. So what is that going to give us? Right, 365.24 times 86,400. So that's how many seconds is in the Earth's orbit. So this looks like 315563736. So 31,556,736 seconds to the year. All right. So take this equation. We're basically trying to solve for the mass of the Sun. So this thing is saying that mass should be 4 pi squared r cubed over t squared g. So 4 times pi squared times 1.496 by 10 to the 11 meters, quantity cubed, divided by this number that we just got for the period, 31,556,736 seconds squared times 6.67 by 10 to the minus 11 Newton meters squared per kilogram squared. All right, moment of truth. Let's plug this stuff into the calculator. So I'm going to go ahead and go out of order here. I'm going to square this thing, so that's the period part of it. 1 over x, so there I've divided by the period squared. Now let's go ahead and multiply by the 4. Let's multiply that by the pi squared. Let's multiply by the 1.496, and that thing is getting cubed. Multiply by our 10 to the 11th cubed. That's what we have so far. Divided by 6.67 times 10 to the minus 11. Get a big number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Thank God it's the correct number. So we get 1.99 times 10 to the 30 kilograms. And if you don't believe me that that's the correct number, then let's look again at that good old table. And the Sun has a mass of 1.991 times 10 to the 30. I'm just going to throw out here as a closing thought on this whole lecture that when you start doing these astronomical things, the math itself isn't necessarily all that hard or all that bad, but there's enough of it that typos will manage to occur all over the place. So those of you taking this class, you are going to have some homeworks at some point or other in which you have to calculate these orbital periods or orbital distances or so on. The math is not that hard algebraically, but there's just enough terms that you have to keep track of, enough powers of 10 and so on, that mistakes may happen when you do these calculations. Good luck to you. I would recommend double checking, triple checking, checking your answers against tables, that kind of thing, before entering them as homework. Hopefully you're using something a little better than the calculator that I'm using on my computer for this. That's the end of this part of Lecture 6. I hope that you have enjoyed this lecture. I especially hope that you found the material to be interesting. Some of it I hope you found even to be fun. It's sort of a different pace than my usual lectures because I kind of wanted to look at some of these fun historical models. And above all, I hope that you find this video helpful. So thanks for watching.